program. So the flight was cancelled, so give a short talk. So I prepared a lot of slides, but I'm going to keep it short. So basically, the idea is to look at the interface of machine learning and algorithmic information theory from the point of view of kernel methods. So that's joint work with Marcus Solomonoff and Ron Wilson. The main motivation was his Marcus paper, philosophical paper on induction and how Solomonoff induction can be used as a practical solution to the problem. So here, so this is more of an experimental argument. So I just want to. This is more of a series of papers. I mean, there have been a lot of notes during the last 2 years. So many parts that you can find on KC-Kernels and ResearchGate. Yeah, have question. Yeah. And so yeah. So these are the so the first 2 papers were accepted physically. The last 3 ones are already submitted. So this one was in preparation. This one was uploaded on ResearchGate. So this is like we talk. I mean, we resonate with many of the talks that we have here about approximation of Solomonoff induction, the link between Solomonoff induction and neural networks. And so the idea here is just to show that kernel methods can be used as a way to connect between 3 areas, like machine learning, algorithmic information theory, and systems. So the reason for this is that kernel methods have been around for a long time, and then there is like a learning theory that was developed from kernel methods by people like Cooper, Smell, and Zhu. I mean, they worked a lot on this for the last 25 years or so. So they even have a book, and so there's an entire learning theory from kernels. And our goal is to see if there is a way to kernelize in way Solomonoff induction. And then from there, we would be able to say a few things from a learning theoretic point of view on Solomonoff induction itself. And so we are going to talk a bit about Solomonoff induction, and then why kernel methods can be very useful in learning theory, and then make the connection between kernel complexity and kernel methods. And then from there, we are going to get like 2 kinds of kernels. So one we call kernel complexity kernel, the other one we call the Solomonoff kernel. So this will allow us to do induction and inference using this kind of kernels. So this also like resonates with Aram's talk, the latest one from this morning, about doing Solomonoff induction with finite data sets. And so the main idea is a sort of projection principle, where we'll be doing so Solomonoff induction. I mean, it doesn't happen in a void, right? And mathematically, there is a mathematical structure where it is happening, and then the idea is to project the mathematical structure into a Hilbert space and then a Banach space, and see what can be done there at the level of induction and inference. So we'll define 2 spaces. I mean, one we call it Solomonoff Gaussian Hilbert space, where we can do Gaussian processes, that we call them Solomonoff Gaussian processes. And then this will be done from covariance matrix. The matrix is combined, computed from program length. And then the other ones will be, we call them Solomonoff Barron spaces. So Barron spaces are basically Banach spaces, which are the native spaces of neural networks with 1 hidden layer. And so here, the learning theory is done through a total variation. So that's the philosophy somehow. So here, as you said, I mean, we have been seeing this kind of description of Solomonoff induction. So the questions that we are asking here is, which target space should receive a projection of M, and which computable family inside the space can stand in for it while preserving what learning task needs. So here we are talking about which kind of learning task we are trying to get with finite data sets. And then, as I said, what I mentioned is that how would Solomonoff induction look like in a Hilbert space, in a Banach space, and then more generally in a metric measure space. So we're going to see actually that 2 kernels that we are going to find. So the Kolmogorov complexity kernel and the Solomonoff kernel are just like two faces of one meta kernel that is showing up in like marginal spaces, which are the metric measure spaces. So we're going to show that the Kolmogorov complexity kernel and the Solomonoff kernel, they differ only by measures. So yeah, so this is what I was saying. I mean, so we start with Solomonoff induction that is universal but uncomputable. And so the whole story of this, like this, what we call projection principle, is to choose a target space where we can do computations. And then the target spaces will be the Hilbert space if we are dealing with program length that are encoded in covariance. The covariance matrices, if it's in a Banach space, we are going to use total variation. And then I said, like unifying between the two will lead us to metric measure spaces, but we can think about other more general spaces like topological spaces. But this will lead like sort of like encoding the inductive bias as we have been hearing inside the space that we are working on. So so that's the main idea. So we'll focus on these two routes. I mean, in this talk. So the first one is the Hilbert, the projection in the Hilbert spaces, where the idea is to work with covariance matrices that preserve weighted feature inner products. And so this gives a Solomonoff kernel with RKHS. The producing kernel Hilbert space is what we are going to call the Solomonoff Gaussian Hilbert space. And then if we do a Gaussian process in the Solomonoff Gaussian Hilbert space, we are going to get Gaussian process where the covariance matrix is encoded by the program length, and we call it the Solomonoff Gaussian process. And the other case is the projection in a Banach space. I said like if this is like the native space for a single layer, like one hidden layer in our network. So these are leading to Barron spaces. So they are basically Barron spaces are just like the natural move from RKHS to yes.
So for Solomonoff induction, we certainly perform Solomonoff induction over something, but the idea is sort of universal, right? So you just encode everything in binary, and then if there's some Gaussian process or something, then that's some computable method that it will learn, right? So I don't understand. So is the goal somehow to improve sequence prediction using something?
Yeah, so function approximation, Gaussian processes, but you just encode the bias inside this kind of learning task.
So it's not so much to improve over Solomonoff sequence prediction, but somehow use Solomonoff induction to improve the kernel methods.
Yeah, exactly. Yeah, so it's like so it's use Solomonoff induction inside kernel methods, or use Solomonoff induction inside like a hidden layer neural networks. Yeah. So just to improve, actually, it's mostly function approximation. We are after function approximation, but we want to use Solomonoff induction to choose the right space where we are doing function approximation. So whether we are doing kernels, so which means that we are going to use Solomonoff induction to find the best Hilbert space where we are going to do function approximation. If it's in the case of one hidden layer neural network, we are to try to find the best Barron space where we are going to do function approximation. It's really about function approximation here. Sorry if it wasn't clear, but it's really about approximation and unknown functions from random samples.
No, that's probably obvious.
Yeah, but it's no, thanks for asking the question. So yes, so I'm not dealing like with everything. It's mostly function approximation.
So would like a potential goal be like forcing the learning to go into like spaces, and I know like good regularizer or like some properties that force those things.
Yeah, exactly. Yeah, so basically just to find. So the whole idea is to find a space where you can do computations and then do the computation. So it's more of like a topological projection as a first step. Yeah. So because we can try to tackle like, okay, why is it uncomputable? So maybe the space itself where some induction is happening is just like just a set. But then assume that this set you're approximating it with a space where there is structure, like a Hilbert space where we have notion of similarity, or like a Banach space where I have notion of distance, or a metric space where I have notion of metric. Yeah, so that's the whole story. Just like project in a space where there is structure, and then you do the learning task. But here it's just mostly, as I said, like functional approximation, and yeah. So this is like so AIT. I mean, I think everybody knows about this. But then you have, as I said, there is this learning theory from the point of view of approximation theory, especially the program of Kupers-Melzu, where they were looking at the spectrum of the integral operator associated to a kernel. And here the goal is to basically find the kernels that are coming from AIT, and then do computation. So basically find an integral operator associated to these kernels, and then have the whole learning theory that was developed by Kupers-Melzu to see how these results will yeah. So that's the story. So I said why kernel methods? Kernels. The advantage that they start with similarity. A kernel is a measure of similarity, but they are not only that, because they are going to define the geometry, which is the Kernel-Hilbert space, and then this will give us a space where we can do predictions. So basically, the way we are approximating functions from random samples using the data that we had. And then from there, we'll be having two kinds of error, which is the sampling error and the approximation error, which is like generalization error. And so this is what the learning behavior is characterized in this case here. So then what we are going to do is we are going to just add extra level here, which is AIT step. So as I said, the kernel is a measure of similarity. And then so the RKHS does the closure of the span of K. And so what the kernel does, as I said, it's not only just a measure of similarity, it's giving us a geometry as well. Yeah. So basically, a kernel turns the chosen notion of similarity into a space of predictors and then define geometry. And then if we are looking at approximation, so this is what your question, like approximating a random function. A function from random samples. So this is what we get. We are going to get a regularizer. And then here, what we are going to get is that we are going to just replace basically this regularizer with an inductive bias coming from Solomonoff induction. And so here in that case, the learning is balancing between like sampling error really and approximation error. And then we get this kind of decomposition, approximation error and sampling error. And so that's choosing the regularization term, basically, which is like choosing the best Hilbert space where we can do computations is very critical. And here the question of how do we choose the best Hilbert space is coming from AIT. So that's the idea. So what Smale did is that they given a kernel, so they have an entire learning theory, as I said, which is basically you take a kernel, you define an integral operator, compute the eigenvalues and the eigenfunctions of the integral operator, and then you define the effective dimension based on the regularization parameter is showing up here. And so that relative to rho, which is the N of distribution and the regularization parameter, is the spectrum of the integral operator describes the RKHS effective capacity, i.e., how many directions are usable and how costly they are going to be. So then you have generally these three universal regimes depending on how the eigenvalues are. And so given these regimes, you are going to be able to, so how many small directions appear, or how many, like only finitely many directions matter, or new directions appear, but they will appear very slowly. And so our goal is just to reformulate this kind of results using the kernels. And then this is also related to the approximation error, basically how well you are going to generalize when it comes to unseen data. So which is characterizing the capacity of the space that you are working on based on the eigenvalues and the eigenfunctions. So basically what we have is that we have kernel giving HK, which is the geometry, then the approximation, and then generalization. So so this is the density. And here the idea is that there is a direct intuitive link between kernels, which are measure of similarity, and relative kernel complexity, because the idea is that if two objects are close to each other, then you can compress them into each other, right? And so naturally, we get this what we call the kernel complexity kernel, which is essentially the exponential minus lambda of the relative kernel complexity. So here, this is the intuition. So the only thing with this kernel is that it's not always positive, so indefinite, so we cannot make of it a good measure of similarity that leads to an RKHS. But this is where we have introduced this. We use this approach called E2KE, which is the distance to kernel embedding, which allows us to make of it a kernel, like a proper reproducing kernel. And this is done through, since we cannot like compare objects to each other, we just want to have these landmarks, which are like random parts, omega 1 to omega n. And then depending on how we are doing with respect to this landmark, we are going to define a proper similarity model. So we end up having proper kernel through this transformation via D2KE. So yeah, so that's the I was saying here. So yeah, so this is like the discretization of the Kolmogorov complexity kernel, and so it asks how similarly x and y are, and how do they relate to the selected landmarks.
So this is just like symmetrizing by have a triangle inequality of the space, because the additional holograph complexity is not symmetric.
So yeah, so it's not exactly symmetrizing, but it's mostly measuring. So because here we cannot do this.
Because the conditional.
Yeah, exactly.
Is not symmetric.
It's not symmetric. Yeah. So the way we do it, just we take like we introduce this random landmarks, and then we compute the distance with respect to this landmark, and then we see how similar they are based on like a referential. So you don't compare them to each other, but you compare them to some external reference. Yeah.
Why are you using landmarks?
What is it?
Why are you using landmarks rather than information distance or something like that?
Yeah, I said because I want to just to make sure that it's positive, like proper kernel, so like reproducing kernel. So because so the information distance is not a proper. It doesn't satisfy the properties of reproducing kernel. So here we are really trying to construct a proper reproducing kernel, so that we can construct a proper reproducing kernel Hilbert space. So yeah, so this is what I was saying here. And yeah, so then from here we get like actually two views, depending on the random landmarks that we are getting. So we are going to get, as I said, this is the Kolmogorov complexity kernel, but then we can also see which landmarks are important. So if we do that, then the measure will be important. And so this is what leads to the Solomonoff kernel, because you are going to have to use the Solomonoff measure in that sense, where we say that we are going to give more weight to shorter descriptions and vice versa. So this is what leads to defining the Solomonoff kernel. Yeah, so this is, so basically we end up constructing Solomonoff kernel as such. And so from there, we are all set. So basically we got Kolmogorov complexity kernel and the Solomonoff kernel, which are like proper reproducing kernel. And then we define a proper AKHS, and then everything else will follow up from Smear's result, except that in that case, everything will be depending on program length. Yes, question.
So in Solomonoff, we have the length of the program, or short length of the program. So I understand what that means intuitively. Where's the 2 to the minus k somehow in k sol?
What is it? What?
Which bit of k sol is favoring? Like, what's the intuition for favoring short descriptions in that second?
Yeah, here in the measure.
So that measure is, but how is it favoring short? Like, what is short in this case?
Yeah, it's this description. So if you have a function.
Oh, it's the same thing.
Yeah. So it's exactly the same thing. We just reformulated things. Yeah. Okay. So this is why I'm saying that I'm just using the same ideas, just like reflecting them in Hilbert spaces and Banach spaces. Yeah.
So here's the similarity, like the algorithmic neutral information, like kind of like.
Yeah, exactly. So actually, so one of the papers is really to show that there is a link actually between the Hilbert-Schmidt independence criterion and this kind of measures. Yeah. So the AMI. So establishing a direct link between the two similarity measures. Yeah. So you see that with the advantage that we are having a proper AKHS and proper geometry. Yeah. And so where you can do like machine learning, like as you know, like kernel method. So yeah, so that's so this is what I was talking about, like if you have KC-Kernels, so it's like it can be uniform or very hard, but otherwise, if you have Solomonoff kernel, you can use the USOL. So yeah, so I'm already running out of time. So let me just go quickly. So yeah, so this is what we get from this kind of results, is that we have one coding language for computable features. We have a quantitative Occam regularization in the kernel spectrum. So basically, we everything that Cooper-Smith zoo is being transferred and rewritten. So it's not a trivial thing, but at least you see the beauty is there. What the Cooper-Smith zoo did before, I mean, is transferred through AIT, and then we get kernel regression, representative theorems, and then effective dimension analysis. And then we have a covariance for the Gaussian process that includes this kind of bias. And so it's so the other thing is that so this is just like shadows of Solomonoff inductions, and basically approximations. But the approximation is more based on a topological argument where we are projecting on a Hilbert space. And so I said from here we are going to get like a Gaussian process that we call Solomonoff Gaussian process, which is basically doing inference in a Solomonoff Gaussian Hilbert space where you have the inductive bias from the beginning. So here, this is what Solomonoff Gaussian Hilbert space is doing. Is by definition, by working in this space, it makes simple directions cheap, and their long description directions are expensive just because of the eigenvalues of the integral operator. And so this is what happens to the Solomonoff Gaussian.
Do you have an approximation of that?
Yeah, so I said, I mean, it's one of the reasons of giving this talk. I just want to see what are the examples that we could. I mean, as I said, I'm coming from the theoretical perspective. I'm still looking for examples. Yeah, but I'm looking forward to kind of. But we have but the theory is there. I mean, the approximation theory is there. But just what's missing is really the application of the examples and where to really see the difference. Yeah. So you see the space he said here. I mean, that's by default is giving. It's wide exactly where the descriptions are shown. So it's not subjective anymore, where it depends on the choice of the kernels. Here, by default, we are choosing the direction where the descriptions are shown. And then we recover the same three regimes of the Cooper-Smith zoo spectral regimes, but using program names. Yeah. So here in that case, I mean, counting how many useful descriptions exist at each reduce the capacity of the Solomonoff Gaussian Hilbert space. And so so then we said we got approximation errors. So we have also a representative theorem that shows up in this case. So this is, for example, the RKHS norm. And now that the move, I said from here we can move to Barron spaces, which is basically you take your representative theorem in RKHS, and then what happens in like neural networks with one hidden layer is that we are learning the feature map at the same time. Right? In that case, you cannot use the RKHS norm, but you use a total variation norm. And then in that case, we get the Banach space instead of Hilbert space. Yeah.
So just as you normally do this, right? You're kind of at time. So if you get the same question.
Sorry?
No, I don't know if you're watching the clock.
I know, actually, I'm not. Actually, yeah. Okay. Sorry. Yeah. Okay. Yeah. So that's Okay. Yeah. So basically, the story, as I said, basically we get like a Solomonoff, and then we are just projecting on different spaces. And each route presents different structures. So each must be judged by the distortion that is native to each category. So that's the story. And so that's all. Yeah, thank you.